Observe this raw electrical arc oscillating between these nodes. This is a high-speed visualization of alternating current, pulsing back and forth dozens of times every second. Finding the average of a static set of numbers, like a month of grocery bills, is a simple matter of addition and division. But an alternating electrical current is never stationary. Its value changes at every infinite fraction of a second, meaning simple arithmetic addition cannot account for every point in the wave. To find the true mean of this moving wave, we have to bridge two mathematical worlds by translating analytical calculus into physical geometry. Understanding how alternating current behaves in our power grids requires us to redefine how we calculate an average within a continuous system. This graph establishes our visual baseline. We have a standard sine wave plotted on a current versus time axis, with the peak current labeled I sub m and the full period of one cycle denoted by capital T. For a continuous function, average current is defined by this integral formula, the integral of the current divided by the time interval. Integrating the current over time is mathematically equivalent to accumulating the total physical area under that curve. The denominator is much simpler. It is the total time interval we measure. This calculus formula provides a rigorous way of saying that the average is the total geometric area divided by the total time. If we apply this logic to a complete wave cycle from time 0 to t, we encounter a logical problem. Because the sine wave is symmetrical, the positive physical area above the axis is equal to the negative area below it. When added together across a full cycle, these areas mathematically annihilate each other, resulting in a net area of 0. A net area of 0 means the average current over a full AC cycle is also 0. This formal rule confirms the paradox for both current and voltage over a complete cycle. While this zero average is mathematically true, it is physically useless for calculating the work the wave performs or its effective magnitude. To extract useful data, we must change our approach and restrict our integration to a single positive half cycle. We start with the trigonometric function that defines the wave. Current equals the peak current, I sub m, times the sine of omega t. We substitute this function into the numerator of our average formula. We set the boundaries of the integral from time 0 to the halfway point, t over 2. Dividing the whole expression by the time interval of t over 2 is the same as multiplying by its reciprocal, bringing 2 over t to the front of our equation. This algebraic setup is now ready to calculate the exact geometric area of the positive AC pulse. To find the antiderivative, we recall that the integral of sine is negative cosine, and the angular frequency omega must be factored out into the denominator. We evaluate the limits by plugging in t over 2 and 0 into our time variables. Solving this requires a critical substitution regarding the relationship between the wave's period and its frequency. Since period t equals 2 pi divided by omega, the complex argument inside our cosine function simplifies down to a clean value of pi. The remaining trigonometry is straightforward. Negative cosine of pi is 1, and negative cosine of 0 is negative 1. 1 minus negative 1 leaves us with a total of 2 inside the brackets. As the constants simplify, we arrive at our final half-cycle average formula, 2 times the peak current divided by pi. This same relationship applies to the negative half-cycle and to AC voltage measurements. This constant ratio means the average of a sinusoidal half-wave will always be exactly 2 over pi times its peak amplitude. Now, consider a different shape, a sharp triangular wave. We can test our logic here without relying on complex integration. The foundational premise remains. The average current is the area under the graph divided by the time interval. Because this half-cycle forms a perfect right triangle, standard geometry can calculate the area far more easily than calculus. Using the area of a triangle, 1/2 base times height, our numerator becomes 1/2 times the base of t over 2, times the peak height, I sub 0. We then divide that total area by the time base, which is also t over 2. The t over 2 terms in the numerator and denominator cancel out perfectly. The result is elegantly simple. For a triangular wave, the average is exactly half of its peak value. When a waveform is constructed of linear shapes, basic geometry is a significantly faster tool than formal integration. Comparing these two waveforms highlight their structural differences. One is defined by a smooth curve, and the other by straight lines. To solve them, we use different tools. integral calculus for the curve, and simple geometry for the triangle. These different shapes naturally yield different constants, with the sine wave averaging to 2 over pi and the triangular wave averaging to exactly 0.5. Despite the change in math, the physics remains the same. We are accumulating total output and dividing it by time. These results confirm that integration functions as a practical method for measuring physical area on a graph, translating symbolic operations into geometric reality. In the real world, alternating current can be distorted or reshaped into many different patterns beyond a perfect sine wave. Memorizing rote formulas for every possible shape is an inefficient way to study electrical systems. Mastery comes from recognizing the geometric shape of the data first, and then choosing the most effective tool to analyze it. If the data follows a curve, use calculus. If the boundaries are straight, rely on geometry. The most complex mathematical proofs are often just precise descriptions of the simple shapes we observe in the physical world.